everyone. So we're going to talk about volume using cylindrical shells. So for this one, you're going to have to already be familiar with cross sections, volume by cross sections before you start this topic. So cross sections are actually where we're going to start with this lesson. So the thing I want to say is that sometimes cross sections can be awkward to use. So here's kind of a classic example. So let's say that I have the curve y equals 2x minus x squared, and I want to revolve it around x equals -1. So let's draw what that looks like. So here's my curve 2x minus x squared, and then here's x equals -1. So if I revolve that about, what it's going to look like is this kind of takes like this like bundt cake shape. Cake. Okay, so now what we're going to do is we want to think about the washer method. The washer method would actually be pretty difficult here for two reasons. So first of all, I've revolved this about something that's parallel to the y-axis. So one thing is that I would have to integrate with respect to y, right? And so since I would have to integrate this with respect to y, what that means is that I would have to solve this equation here for x. And that is not necessarily the easiest thing to do in this case, to have two x's in that equation. So this would be kind of awkward to use. The other thing that is a problem here is that think about my outer radius versus my inner radius. Here would be my outer, here would be my inner. This is literally the same curve, right? So there's this whole like awkwardness in trying to use the washer method sometimes. And so really there's another way to do this, which is by cylindrical shells. So there's a difference between a washer and a cylindrical shell. So a washer, we've seen this now in calculus in a few different ways, but a washer can really take any shape that you want. So I've got these two awkward walls here. A cylindrical shell is always referring to kind of the same shape. So you could think of this as like a paper towel tube, or you could think of this as like taking a piece of paper and then rolling it up. That is what makes a shell shape. So it is like this hollow cylinder, okay? So with the washer, the big thing, right, is that we need to know that there's an outside radius and an inside radius, and they really need to be two separate things, right? If they're the same equation, that's going to cause problems. With a cylindrical shell, this is not really an issue. So the thing with a cylindrical shell is, so again, if you think about it as that analogy of a piece of paper, you could really unroll that, right, to help you figure out what the volume is. And so the volume of this would be 2 pi because it's circular, but then the rest of this would be the length times the width times the height. That would be how you would find the volume of your cylindrical shell. So if we go then back to how does that fit into our example? So remember, the way that this works, so I kind of colored this around for a minute, right? So this thing has this giant hole in the center, and you have all these outside walls surrounding it. Again, it's probably better to actually look at a piece of bundt cake to kind of reference this. So think about if I could shove pieces of paper, like hollow tubes, into this, but I conform them in such a way around this so that I could fill the inside of this. So using this back to this picture, so what would that look like? So what we would think of is I would take like this hollow tube inside of the bundt cake, and this would be one shell inside of the bundt cake, okay? So the thing is, so I can find the volume of this one shell. And if I can find the volume of this one shell, then I can start to put more and more shells inside of this. So imagine this now. So imagine that you keep taking your paper and you keep basically rolling more and more paper around each different paper, right? So what we could slowly do is we could take those tubes and put one tube inside of another. So you can see I've got the pink tube, the green tube, and now this like yellowish tube. Those are all fitting inside of one another. And so what I can do is I continue to fill this in until I've filled up my entire bundt cake with all of these different tubes, okay? So this is kind of the idea here. But I want to go back to thinking about just one shell for a moment. I want to think about labeling this. So if I think about labeling this, so the radius of the shell will be found by taking some point kind of inside of this bundt cake to the radius. So that is a length of whatever this x value was in here to the radius. That would be minus -1 in this case. If this doesn't make total sense, I'll show you another example in a second. So just kind of go with me for a moment, and then we'll look at some other examples. So that would be how I would get to the radius versus the height of this. The height of this is going to be, so wherever that tube is sitting against the curve, so each tube is sitting at the top of the curve. So the height of each tube will be dictated by our function, 2x minus x squared. And then the width, so the width is ideally as small as possible. And so what we typically do as a trick in Calc 2 is we say, call the width right now delta x, and we'll see what we do with that in a second. So we'll use that to help us ultimately get to an integral. Okay. So what I want to do is, so I just want to state that similar to cross sections, so a key with using shells is that you can use various levels of thickness. And so since I can dictate these different thicknesses, that means that once again, there is another Riemann sum associated with our shells. So we can really think of our shells as just being this sum of adding up a bunch of different volumes. That's what this Riemann sum here means. Sum up all of the different volumes. So we had this here. I can continue to expand this until I have an infinite number of shells kind of shoved into this thing. And all my volume is just adding up all of those different ones. Of course, we have also talked about how to actually find the volume of each shell. So we want to get a little bit more refined in our formula. So instead of writing just this general volume formula, I can write out the volume formula that I had, 2 pi LWH. Okay. And we also just talked about, right? So we talked about how to find that length, that height, and that width. So in this case, so I have my length was that radius, right? So that was x plus 1. My height was dictated by that 2x minus x squared. And then I had that delta x for the width. Now, since I am presently dealing with a Riemann sum, I have to index these x's by a k. So that's going through each different x that we set as we go along. But now that I have a Riemann sum set up in this way, basically what that means is that there is an integral that is equivalent to this. And that integral can be written as 2 pi x plus 1, 2x minus x squared dx. So the dx is kind of standing for this notion of like this thickness delta x. We want to make that as thin as possible. And so the way that we make that as thin as possible is we basically like take the limit of it, right? So that's where all the limit fits in. So all of this kind of goes back to having this infinite sum with integration. And of course, now that I have the integral, I can just multiply everything together. And the reality is like, this is actually a pretty simple integral. The hard part, right, is of course setting up how to do this. So from here, now I can go ahead and just integrate. So when I integrate this, I just get 1/3 x cubed plus x squared minus 1/4 x to the 4th. And then I can plug in my limits of integration, and ultimately I will get 16 pi over 3. So you can see all my work here if you want to pause and write it down. Okay, so this is one example of working with cylindrical shells. So I want to just take a moment now to appreciate the formula. So for a cylindrical shell, so if you are rotating about a vertical line, so that's anything of the form x equals L. Alternatively, you could think of this as anything parallel to the y-axis. So this is going to then be integrated with respect to x. So we rotated about something parallel to the y-axis, and we integrated with respect to x. And it's always going to be this idea of just find your radius, find your height, and you've got everything that you need to do. And of course, if you were to integrate the other way, so now let's say that I want to integrate any, instead of vertical line, let's say that I want to do a horizontal line. So if I want to do a horizontal line, now I'm going to integrate with respect to y. So the thing about this is that shells kind of integrate with the opposite variable. And just to give you a visual of that, so if my shells, what am I trying to say? If my revolution goes this direction, so something that is parallel to the x-axis, then you have to integrate with respect to y. So that's what I mean, like shells integrate with like that opposite variable. It kind of works in the opposite way of the disk method or the washer method. Okay, the other thing I want to say about the radius is, so if you're just going around the axis, you don't have to worry about adjusting the radius. If you just go around the x-axis, then you will just use y as your radius. If you go around the y-axis, then you will just use x as your radius. But in the event that you're going around a line, so then you have to think about the highest versus lowest point always when you set up your calculations. And this is really just something from algebra. So what I mean is, so I have two line segments here. So if I just asked you out in the wild to find the length of the the line segments, you would tell me to just take the highest minus the lowest point. So in this case, this would be a minus b, or here that would be c minus d. So this is the same concept in the shell method, believe it or not. It's just now you have to just stay oriented. So it could be in the shell method that now you are like rotating. So maybe you have, let's see. So let's say that I'm rotating about this line B, and then let's say I have some other curve here. So I could think of this as, so my radius maybe could be like trying to find this calculation here. So this would be whatever, I guess in this case, since we're going this direction, so this would be the calculation y minus, or x minus b. That's what it would look like in a shell method problem. Versus if we're going this direction, it would be y minus d in this case. So that's kind of the way that you want to think about everything, is you're always just kind of orienting yourself with highest minus lowest. So now let's actually talk about some other situations here. Okay, so we're going to find the volume generated by revolving the bounded region about the y-axis. Okay, so when you are rotating something about a line, so remember it was some line x equals L. So this is really anything that's parallel to the y-axis. So one of the things that is different with the shell method versus the disc and washer method is that when you go about the y-axis or parallel to the y-axis, you integrate with respect to x. So in this case, I'm rotating about the y-axis, and so that is going to then be integrated with respect to x. So first things first, we want to, of course, draw our region. So I have my line y equals x right here, and then I have my line y equals negative 1/2 x. So there are my two lines. And then I have the line x equals 4. So x equals 4 will be right here, and so this is the region then that we are rotating about the y-axis. So when I rotate this about the y-axis, it's still that same kind of dynamic of, so I'm going this way, right? So I'm going to have some region that when I reflect it over, it looks something like this. So I have these little walls out here, and then I have this like divot in between. Now, since I'm rotating about the y-axis, so this is something that you just kind of have to get in your head. It's the difference between the disc and washer method versus the shell method. So in this case, I'm going to be integrating with respect to x. So I want to just go ahead and set up that formula first and foremost so that I don't forget which variable I want to integrate with respect to. Okay, so now let's talk about filling in this formula. So once you have your rotation, the rest of this should really come together. Now, as far as finding the radius goes, so in general, when you rotate about an axis, you don't have to really worry about this. So in this case, my radius, the radius of each individual shell, it's just going to go from here to here. This is just going to be x, and that's like something that you can just kind of rely on. So it's wherever you are choosing in here, minus 0, so it's just x, okay? So the radius, the short story is, if you just go about an axis, it's just going to be x. Now for the height. So my height now, this is where you've got to kind of pay attention. So for your height, now we are thinking about that highest minus lowest calculation. So my height is dictated here. So I have this curve here dictating one height and this curve here dictating the other height. So to get to the height in this case, what I need to do is I need to take that highest curve minus that lowest curve. The highest curve is this here, this was just x. And the lowest curve is this one, negative 1/2 x. So that is going to be what we're going to input into the formula. The other thing that I just want to note here is I also want to take a moment just to note what are my points of intersection. So since I'm integrating everything with respect to x, looking at my points of intersection, what I'm interested in is what is my lowest x point and what is my highest x point, because that's going to be what I use for my limits of integration. So I've actually now got everything I need to fill in this part of the formula. So this is going to be 0 to 4, 2 pi x times 3/2 x dx. And so from here, now we can just go ahead and integrate this. So I can just now set up this integral. And of course, to integrate this, so I'm just going to multiply those two things together so that I just have 3/2 x squared. And then I can integrate this. So I'll have 2 pi times 3/2 times 1/3 x cubed, and I need to fill in from 0 to 4. So then what I can do is I can, of course, just rewrite this as, so you'll notice, right, that all my 2's and my 3's drop out, so I'm just left with pi x cubed. So if I plug everything in, I get 64 pi. Okay, cool. So now what we're going to do is we are going to now slightly change this up. So we're going to find the volume generated by revolving the region about y equals -1. So now we're just going to throw it straight into something that's a little different. Okay, so first of all, of course, first we want to draw our region. So I have my x equals 1/2. And so I've got my x equals 4 and my y equals 0. So we have this little triangular shaped region. So this is what I'm going to be rotating. And my line y equals -1. So where is that? That falls underneath. Okay, so when I rotate this or when I revolve this, I get this shape here where I have, so just to kind of keep us oriented here, so I have these walls kind of on the outside. So those are my solid walls. And then the rest of this, we just have like this like big tube center in the middle of everything. Okay, so a couple of things we want to notice with this. So in this case, y equals -1 is parallel to the x-axis. So you can see right away that this is very different from the previous problem. In the previous problem, I was rotating something that was parallel to the y-axis. So now that we're going to something parallel to the x-axis, so what do you think is going to happen? In this case now, we flip everything and we're going to integrate with respect to y. So the shell formula, when we revolve about horizontal lines, that means that everything now gets integrated with respect to y. The way that I personally remember this is I just remember if it's parallel to the x-axis, then I integrate with respect to y. So the shell formula, like the way I kind of remember it, is that it is you integrate kind of in the opposite from what you would have done from the disc and washer method. So for the shell method, if you're revolving about something the x-axis or parallel to it, then you integrate everything with respect to y. Okay, so back to this. So what we're going to do then is we're going to fill in this formula. And so the other thing I kind of want to talk about here is orientation. So I want to have this in front of me while I'm talking about this. So my formula here is I'm integrating everything with respect to y. I still need to find the radius. I say this is height. We'll talk about this in a second. So first let's talk about the radius. Okay, so using this picture here. So my radius is going to be dictated by some point in here going to some point down here to this line y equals -1. So that is that situation that we were talking about a second ago. Remember where I was talking about how you're just trying to figure out your high minus your low points. So when you are trying to figure out your radius calculations, you want to think about what's going to be, what kind of represents your highest versus your lowest point. So in this case, everything has to be done with respect to y. I know that this gets kind of confusing, but what we're doing here is, so we're choosing the highest y point. That highest y point is going to be dictated by some place in the green region, right? So I didn't color it for now so that you can see what I'm doing. But the highest y point is, it starts at some y here, and then minus the bottoming out point, which is -1. So my radius in this case will be y plus 1. Okay, so there is our radius portion of this. And then I need to figure out what is, okay, so there's two different ways of how you can think about this. So when I initially talked about this when we were oriented one way, I said that you figure out the shell height. So you could, when you are integrating now going this other direction where we're oriented this way, I think that there's two different ways to think about this. I like to think of everything in terms of height, and basically I guess what I try to do is I just reorient myself. So this is the height if I turned 90 degrees. But some people prefer to think of this when they integrate around the, when they're integrating with respect to y, they prefer to think of this as width. So it doesn't really matter how you want to think about this. I just need to know, how do I write this calculation here going from one way to the other? And so the thing to remember now, right, is that we are always going highest minus lowest. So to get this width or this height or however you want to think about this, this is going to be dictated by, here's the highest point, here's the lowest point, somewhere over here, right? So for my height, so my highest point is going to be dictated by this wall here, which is just 4. The lowest point of these different heights will be dictated by where I am on this particular curve. So this length here is this curve 1/2 y. So this will be 1/2 y. So there's my height. Okay. So I've almost got everything that I need. The last thing that I need to know are my points of intersection again. So this point here, this is 0, 0. This point here, let's see, what is this? This is 4, comma 0, and this is 4, comma 8. Okay, so now I've got everything that I need. I've got all my different points of intersection. So the last part of this, right, is I need to figure out just what do I integrate with respect to. And in this case, since I'm integrating with respect to y, I'm looking for the highest and lowest y coordinates. So 0 is the lowest y coordinate, 8 is the highest y coordinate. So I'm going to integrate from 0 to 8, 2 pi. My radius we just said was y plus 1, and my height was this 4 minus 1/2 y dy. So now I've got all the pieces of this here. Okay, so now we can go ahead and we can integrate everything. And so, of course, then I'm just going to FOIL everything out. So I've got everything FOILed out like you see here. And so if I collect my like terms, so what I get is negative 1/2 y squared plus 7 over 2y plus 4. And so then when I integrate that, so again, the integration is usually the easy part. It's like setting it up that you've really got to wrap your head around. So I've got everything integrated out, and then I can plug in my 8. So I get 352 pi over 3 for this one. Okay, so that is the basics of working with these cylindrical shells. So I like to keep these lesson videos short just to kind of introduce you to the concept, but I think you might want to watch more examples. So just keep in mind that I do have more example videos to kind of fill this in if you feel like I didn't show you enough examples. I also have one mega video talking about the differences between the disc, washer, and shell method and all the different ways that you rotate axes. So check those out if you're feeling like you're not totally sure. If you found this helpful, I'd love it if you hit that like button or the subscribe button. And otherwise, I will talk to you guys in another video. Bye.